Another application of the chain rule will be related rates problems. So these are going to be a special type of word problem. So we're going to have a method that's going to let us tear these down from start to finish. To start off, whenever I have any word problem, I read through it first, try to get a feel for what we're trying to do, and try to figure out what I'm trying to solve for. So we're going to read through. If I have a picture that goes with the description of the problem, I draw it. I'm going to extract every bit of information out of the problem, put it off to the side. On my picture, I want to label whatever variables show up, and I want labels for variables that don't show up, but we may guess we may need later on. Now, something special to a related rates problem, the item that I'm looking for is going to be a rate of change usually. So there's going to have to be another rate of change somewhere in the problem, and I'm going to want to link the variables that show up in the two rates of change. So somewhere in our problem is going to be some equation that links these two variables, possibly more than two variables, but usually just two. What I'm going to do then is I'm going to take that equation and then I'm going to take a derivative of that thing with respect to whatever our independent variable is. Usually it's going to be t, sometimes it's x. When I take the derivative of the equation on both sides, we're going to use our chain rule usually. That's how our two rates of change are going to come out of the problem. When I start taking derivatives, the dx dt or dy dt or whatever is going to come out that way. All right, then you're going to want to isolate the rate of change that you're looking for. The items that show up when you isolate, we may be given all of them. We'll be missing a few sometimes. Since given a word problem, I can be guaranteed that somehow I'm going to be able to find all the missing items. That's going to let me find my final answer. For my final answer, since we're usually going to be dealing with physical problems with related rates problems, you want to make sure your final answer makes physical sense. So that'll be, how do you interpret your final answer? The problem is, a stone goes into a pond, a ripple is going to expand. When the radius of the ripple is 2 inches, the radius is going to be growing at a rate of 10 inches per second. How fast is the area enclosed by the ripple increasing? So, related rates problem, I want to read through first, get an idea of what's going on, draw a picture, extract all the information. So a ripple is going to be a circle, and then we'll draw in its radius, put an R on it to name it. Next, okay, we'll call the time where all this is happening, call that t0. So t0 isn't actually going to show up as a number in the problem. We're just going to use that for bookkeeping. So at t0, that's going to be where the radius is 2 inches. So that means R of t0 is going to be equal to 2 inches. So that's right there. We're also told at t0 that our radius is increasing at a rate of 10 inches per second. So increasing tells me rate of change. That's the buzzword. Increasing, decreasing, how fast, how slow, how large. So rate of change, change the radius, so that's going to be dr dt at t0 equals 10 inches per second. Right there. Now, finally we have how fast is the area expanding at this point in time. How fast indicates a rate of change. We want to know how the area is changing, so that's going to be dA dt at t0, and that I don't know, that's what I want. Now also note, by the way the rates of change come out, our variable is going to be time. So everything depends on time, meaning our area is a function of time and our radius is a function of time. So also, when I do derivatives, I know it's going to be derivative with respect to t. All right, next step, we need to find an equation that links our rates. So the variables that are in our rates are going to be area, right there, that's what I'm looking for, and radius. So we need to link area and radius for a circle. Well, we know that that's area equals pi r squared. And we'll put the t's in just to highlight that they're functions of t. Next step, I'm going to take the derivative of both sides with respect to t, and we'll have to apply the chain rule when I hit that r squared. So on the left-hand side, we have dA dt. On the other side, I'm going to have pi. Derivative of r squared is going to be 2r, and then times the derivative of r, so it's going to be dr dt. We take a look at our equation. Okay, we're missing dA dt. That's fine. That's what I'm looking for. R is given to us as 2 inches, and dr dt is given to us as 10 inches per second. So there are no missing variables, so my number for my answer comes right out. So we'll have dA dt at t0 is going to be equal to 40 pi inches per second. Last thing I need to check, does that answer make sense? Well, dA dt is our rate of change. It's a positive number, which means it's an increasing rate of change. So that means the area is going to get bigger. And that totally agrees with what we would think. If I put a ripple, okay, I have a ripple that's going to expand, the area gets bigger. So at least we know that the sign on this thing is correct.